Number 15. Water emerges straight down from a faucet with a 1.8 centimeter diameter at a speed of 0.5 meters per second. Because of the construction of the faucet, there is no variation in speed across the stream. Letter A. What is the flow rate in centimeter cubed per second? All right. So here's a little picture up here. We have the faucet in this location. There's a certain volume flow rate that is exiting the tube. They mentioned that we have to solve that. All right, that's essentially what this is. This is a volume flow rate. That's Q, and they tell us the velocity of the fluid and the diameter of the tube. Right. So this part A, should be fairly straightforward. You're thinking about how are these variables related to one another, and they give us a velocity and a diameter, which probably tells us we could probably find the area, right? And they're asking for Q, so I'm going to start with this equation over here, right? That it says the volume flow rate will be equal to the area, cross-sectional area of the tube, that is, multiplied by the average velocity flowing through that cross-section. So now, in order to find Q, I need to know these two pieces. Let me expand on the area first. We know it's the cross-sectional area of a tube will be a circle, so this becomes pi r squared. Then multiply that by V. Now, I almost have everything I need, right? They told me the diameter. By the way, I converted this into meters. All right, just simply divide this value by 100 or move the decimal 2 places to the left, whatever floats your boat. And now what we need to do is simply take this value, convert it into the radius. So we just take this and divide it by 2, right? So that's what I'm going to do in my equation. So it's going to be pi now multiplied by this diameter, 0.0180 all over 2, because that's the radius now. That's squared. And then multiply that by the velocity, which they told us was 0.5. All right. And also what they were talking about up here, if in the brackets here, because the construction of the faucet, there is no variation in speed across the stream. In reality, all right, when you're looking at flow, through a tube here, there's always, we're thinking it's perfectly frictionless. That's basically what they're saying here, that there is no friction between the fluid. I guess it's, I don't know, did they say, yeah, water, between the water molecules here and the sides of the tube. Now, in reality, we know that that's not true, okay? And you get more friction at the edges of this tube than you would in the middle, right? Because the water molecules here are not rubbing against the side. So what happens in reality, you get faster flow down the middle than you would around the edges because there's less friction. Now, again, just like in most physics problems, we have to make certain assumptions to make the problems calculable, and that's one of them here, all right? So let's try to solve this. If I knew where I put my calculator there. Oh, here it is. All right. Found it, guys. Don't worry. Don't fret. So now here we'll take pi, multiply it now by, in parentheses, 0.018 over 2 squared times 0.5. And we get a value now. The Q is going to be, the volume flow rate is 1.27, right? 1.27 times 10 to the minus 4, all right? Now, if you notice, this will be in terms of meters cubed per second, right? Because I had meters for my diameter, which I converted into a radius. Here's meters per second. So now what I need to do, this is an answer, but they wanted it in a specific, with specific units, excuse me. So we just need to now do that conversion, all right? I'm going to do the conversion up here on the left. So we have 1.27 times 10 to the minus 4th meter cubed per second. Now what I need to do is get rid of meter. So meter goes on the bottom, centimeter goes on the top. All right, plug in your values, right, that there's 100 centimeters in 1 meter. And you have to square this, cube now this entire result. All right. Please do not write, when you're doing this, please do not write meter cubed and then centimeter cubed here and then write 100 to 1. That is not true. That is not the relationship. All right, please just start with your basic conversion, that 100 centimeters is equal to 1 meter. And then you can either now write this out, this literally the same thing, 2 more times if you wanted. All right, then you notice there'd be 3 meters, right? They would cancel the 3 meters up there, then you'd have 3 centimeters, blah, 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 okay? Or you just take this thing and you cube it, all right? So now that we have that, let's do that. So we take our answer, multiply it by now 100 cubed, basically. And here we have 127, all right? 127 cubic centimeters per second. All right, that will be the final answer. So I'll write that over here now. So Q here for the first part is 127 cubic centimeters per second. All right, great. That takes care of that. Now, letter B. So letter B, it says now, what is the diameter of the stream 0.2 meters below the faucet? Neglect any effects due to surface tension. All right, again, some simplifying assumptions. Now, you might be saying to yourself, well, all right, can I use that equation of continuity that says that the volume flow rate, moving through this portion of the tube is equal to the volume flow rate, moving through that portion of the tube? And I mean, you could, right? You can. We haven't violated any laws here. What's the problem though with doing that, right? Let's pretend that this is location 1 over here, and let's pretend that this is location 2 over here. So if I then will say Q1 will equal Q2, right? I just solved Q2, so I know that, right? I probably would use this value though, because it's in the standard units. So I know this value, right? So I'd have to break up my Q1, right? I'm asked to find the diameter, so I'm probably going to have to find the area in here, right? I got to do a substitution, bring that on in. All right, realize that this is the area of 1 multiplied by the velocity of 1. And that will then equal Q2, right? Which I just found. Okay, that's this value. Now what's the problem here? Well, the problem is this. Do you know the area? No, right? They're asking us to find the diameter. So, and it doesn't tell us anything about area. So we have no idea what this is. And do we also know the velocity in this particular section? No, we don't, right? We do not know the velocity of the water through this part of the pipe. It is not the same as this velocity because we're assuming that the diameter is changing, right? I mean, it doesn't tell us that it is or it isn't, but I can't assume that it is the same. So that being the case, right, I cannot use this equation at all because I don't have enough variables. I don't have enough knowns, I should say, to solve for the one unknown, meaning the diameter. The distance, diameter, right? Yeah, so let's solve it now. So how do we solve it, right? So how do we actually do this? Well, the other formula that we can use to help solve this is going to be Bernoulli's equation, and that's the formula down here on the right-hand side, right? If you were to think about this, right, pretend, this is a fluid flowing through the pipe over here, all right? This equation, Bernoulli's equation, is basically like conservation of energy, all right, but for fluids. So if you were to think about, this particular problem, but just in a context you might be more familiar with, right? You might say, well, here's a ball, all right? It's going to start with, some, initial velocity or whatever. It's going to travel up and it's going to reach, this particular height, let's say. And, it'll have some velocity over here and I want to try to find the height difference. Okay, you might say, oh, right, the energy here equals the energy here, right? The kinetic plus the potential will equal the kinetic plus the potential here, right? You set all your equations up. We've done plenty of problems like that. And you'd solve. That's literally, that is now the same idea as this equation is for fluids. This is Bernoulli's equation, and it's the same idea, okay? Just with different variables in there because we're dealing with fluids, but it's the same concept, all right? So now, that being the case, we can now use this Bernoulli's equation to help us solve. Now, I'm not going to write this whole, well, actually I will this time, but a lot of other problems, I'm probably not going to write out the whole thing. So this says that the pressure, okay, the absolute pressure located at the first portion of your tube or your problem, wherever that is, right? It's like the initial state, right? I'm calling this my, initial state. Then 1/2 times the density of that fluid, right, multiplied by the velocity of that fluid at that particular location, plus then the density of the fluid multiplied by gravity multiplied by height, all right, at that particular location, will then equal all the 2's, right? The absolute pressure at the second part, right, plus then 1/2 density times V2 now squared, plus then density times gravity times height 2. If you notice, doesn't this look strikingly similar to the kinetic energy formula, right? Translational kinetic energy, 1/2 mv squared. Doesn't this look strikingly similar to the potential energy formula, right? mgh, this is just rho gh, right? So there is a lot of similarities between this and, like I was mentioning before, the conservation of energy. Now, in order to solve this problem, we have to make a couple of assumptions as well, okay? Otherwise, if I don't, then I have no idea how to solve the problem, all right? The thing is, now you might be saying, well, what about these pressures, okay? It doesn't tell me anything about the pressure of the first part in relation to the second part. It says nothing. Now, I know that this, well, actually, I do know something about the second part. Let me say that. So the fluid here is coming out of a faucet, right? I'll assume it's at sea level or whatever. So I know that the pressure at this part of the tube would be equal to basically atmospheric pressure. All right. But I don't know anything about this, right? I don't know anything about the pressure for the first part. I don't know if this tube is open to the atmosphere somewhere on down the line over here, in which case then they would both be equal to the atmospheric pressure. I don't know if that's the case or not. But if I don't make the assumption that these two pressures are equal to atmospheric pressure, I can't solve the problem. So I have to make that assumption. So if the pressures are equal, then they can cancel from the equation. You also will notice that we're talking about water, and the density of the water isn't really changing. Remember, in theory, that's in theory not true, but, right, because we've done problems in the past now where we were talking about what's the density of the seawater, at the bottom of the Marianas Trench, right, that's 11 kilometers down, and we realized that, well, it actually does change, okay? But in this problem, the density change for water from this location to this location, we're talking about 0.2 meters, is basically a non-event, all right? It will not influence your values in any appreciable way considering significant figures. So the densities are constant. What that means now is, look, all the density was in every equation, so I can cancel that out, right? So now what am I left with? Well, now I'm left with this. So I have now 1/2 v1 squared plus g times h1 will then equal, okay, 1/2 v2 squared plus g h2. Now, how about these? Okay, great. So we want to find, right, what's the variable of interest? The variable of interest is v1, right? I want to find, it's not, it is v1, but it's indirectly v1. So now, if you think back to what we've done before, I know we want to find the diameter, all right? But the variable of interest right now in this formula is going to be v1. The reason being is because, remember what I just said before, that we said that the q of the first location will equal the q of the second. But the problem was when I realized I can't solve this thing because I didn't know a1 or v1. But if I do know v1, then I can find a1, right? Because remember, the q2 was this value. So that's my whole goal here, all right? That's the goal. That's why I'm solving for v1 here, all right? So my whole goal is to solve for v1, and I'll probably do this algebraically and then plug it all in. Now, that being the case, all right, so this is the variable of interest at the moment. Now, what about height 1? Well, remember, this depends on how you frame your problem. You have to start, right, your coordinate system, so to speak, has to start at a certain location. I'm going to choose to start the coordinate system down here, all right, where I'll take this height to be 0, and then this height up here would be now a positive 0.2. All right, so it all depends on where you start your coordinate system. But I do know this value, right? It's going to be 0 from my assumptions, right? I started my height here, okay? So this whole term cancels. V2, we do know what it is, right? What's the velocity coming out of the faucet over here? Oh, look, there it is, wunderbar. And then how about height 2? I just spoke about that, right? So we do know that it's going to be 0.2. Okay, so now this will work out to be 1/2 v1 squared is equal to 1/2 v2 squared plus g times h2. Now, I got to solve this thing for v1, right? So just simply multiply both sides by 2, all right? So I'm going to do that right now. So I'm going to erase this, right? Multiply this side now, just shimmy it on over slightly. Multiply this side by 2. I can distribute the 2 if I wanted. I'm just going to leave it as like, you know, something like this. And then what I had to do is get rid of the square, so I got to take the square root, right? So if I take the square root of this, say bye-bye to the square, all right? Also say bye-bye to one of the lines of the equal sign, but that shouldn't have happened. And then take the square root of the right-hand side as well. Okay, so now, since I did take that square root, I got rid of the square sign. This is what I'm left with, right? Here is V1. Now, since I know this equation, right, we can go back and think about, maybe I shouldn't have erased it, but I should have left this up, that Q1 would equal Q2. This is exactly what I've done before. Then A1 times V1 would equal Q2. Remember, this is Q2 because this is the second part of my equation. Now, I just found an equation which I know all the values for V1, so guess what I'm going to do? Plug it on in, right? And then solve it for the area, break that down, find the diameter in there, and so on and so forth, okay? So let me do actually one more step. Let me divide this by V1. So this would be A1 now is equal to Q2 over V1. And then I can now break up this area, right? So let me see if I can move this. Give me 1 second. So let me just move this up a little bit. And now the area here, remember, it's pi r squared. All right, so we can, right, this is equal to Q2 over V1. I can divide out now the pi, all right? So if I divide out now the pi, that would then be this whole thing divided by, right, pi, which is essentially meaning that it would live in the denominator, all right? I'm going to erase the pi now. Hopefully this algebra is good. And then I can take the square root, right? Then I can take the square root of both sides, and when I do that, I can then get rid of the square here, all right? Take the square root of that. And look, this is what we got, okay? Now that's the radius, and you know now, right, in order to if this is the radius, to find the diameter, I just got to take this thing and then multiply it by 2, okay? And that would then be my diameter. So here's the equation for the diameter, okay? So now I'm going to take that, I'm going to plug it in down here at the bottom. So D is equal to square root, it's going to be square roots and square roots. Q2, okay, so this is going to be Q2 divided then by V1, and this whole thing is V1, so let's plug that in. So we got square root, right, of 2 multiplied by 1/2 V2 squared plus GH2, all right? Great, and then times pi, right, times pi down here, not under the square root, and neither is this, so now we'll take that result and then multiply this by 2. So this is your equation, all right? Some professors like to just see the equation and then you get full credit, or some even give extra credit for the equation. So now let's plug in the numbers though, all right? So we have our Q2 now. Oops, 1 second. Q2 is going to be, remember, meters cubed per second we need, so 1.27 times 10 to the minus 4th, divided then by square root, oh boy, right, of 2 times 1/2. Sorry, guys. Yeah, 2 times, where should I do this? Yeah, I think you guys got me here. 2 times 1/2 multiplied by V2. V2 was going to be 0.5, right? 0.500 squared. And then plus now G, so that's 9.8 times the height of 0.2, all right? Times then, and this whole thing is still times pi, that whole thing multiplied by pi, so just be careful there when you plug it into your calculator, and then multiply it by 2. Let's see what we get, okay? I'm going to simplify the denominator first. So let's just do the 2 times then parenthesis, 0.5, that's 1/2, multiplied by V2 squared, which is going to be 0.5 squared, and then plus, I did minus instead, plus now 9.8, multiplied by 0.2. Okay, let's get that result right there. Okay, and I think I forgot a parenthesis in here if I'm looking at it properly. Yeah, I forgot a parenthesis right in here, guys. Not that it really matters, but I'm just going to keep it consistent. I need one more parenthesis. And multiply by 0.2. Close those parentheses. Okay, now I'm going to take the square root of that. Great. So I got like 2.04, blah, blah, blah. Then I'm going to multiply that by pi. And I got my denominator value of about 6.415 or so. Now I'm going to take the 1.27 times 10 to the minus fourth and then divide it by that value. And then I got to take the square root of that value of 1.97 now, approximately. So now I get 0.00444. And then take that and multiply by 2. So here we go, right? So here's the diameter. The diameter now, and this is in terms of meters, so there's going to be 0.00890, it looks like 890 with 3 sig figs, and this is in terms of meters. So this is the diameter. If you got to convert it to centimeters, I think you guys know how to do that. Multiply it by 100. Whatever value you got to convert to, it should be fine now. All right. Yeah. So, guys, thanks for tuning in. All right, long problem, but important problem because it talks about a lot of different concepts here. So I do hope this helped. I really appreciate your viewership very much. Thank you for taking the time out to watch our videos. And also be proud of yourself too, because you're putting in the work. All right. Nothing great is achieved without hard work. So keep working hard. All right, guys. Thanks for tuning in. Please remember to subscribe. We'll see you next time. Take care.